Yeah. For chain rule? Yeah. I hope the sound and the voice match. It should, if you look at the video from Fahad's class, the recent video, not the old video, the recent one. So if you type in, I'll show you now before we continue.
Into your
Beautiful YouTube channel, yes. And you can see me and my videos, yes. I'll show you just before we start. YouTube.com Okay. So make sure, look, I had Karar searching here. No. Search here, this button, to search my channel, okay? And type in Maths for Engineering. Okay? And then if we go down, keep going. Keep going. Oh, too far. Hang on, let me type in chain rules so I don't have to look. Maths for Engineering chain rules. So Maths for Engineering chain. There we go. So this video, the sound should work on it because it's a new video. Okay? So this is the... Yeah, when I did it with Fahad and Karar. You remember them? Yes? You can probably hear me getting angry at them as well. Yeah. So just so you know, my new videos, I type them in this form. I type the subject, if it's a lesson or if it's a tutorial, the chapter, the lesson, and then NCUK. So if you see the name like this, it means it's a new video. The sound should work fine, no problems. Yeah, with the vertical lines, yeah. Yes. Okay. Can I...
Also usable like physics.
Oh yeah. So like for example, what are we doing in physics? This is materials. So if I type in physics materials, yeah, no, not by this. Wait, am I searching the channel? No, I'm not. I'm searching all of YouTube. Sorry. Yeah, if you want my physics one, just type in physics materials. So you can see there's the tutorial on density, and here's the one from yesterday, 15 hours ago. No views. States of matter, no views. Lecture, 2 views. That's nice. Yeah, so just type it in, but make sure you search my channel. Okay. All right. Let's. Yes.
Last question. How did you get the answer?
For which part?
The last part.
But I.
Use this way.
Yeah, no, but can I write here? So. Yeah. Use this. Which answer? This answer?
This is your answer. This is the formula. Writing for you and writing.
Oh no, you missed a part. There was a minus here.
Yeah.
But
the answer is minus because it's 150 something. This part.
Wasn't it?
I don't know. Are you
No.
answering?
Here, this is what it should be. 150 minus this number. There should be 150.4 minus this number.
It's 6 minus
Yeah.
this one.
Yeah. Oh, you did.
Yeah, I did.
Okay. This one is bigger energy.
Bigger energy.
Smaller energy. And they got the energy of the work. Yeah. It's okay? Yeah. Alright. Can you write this down? I think you might do this in chemistry, I don't know. Ideal gas law.
No.
You might do it, not you have done it. Got it?
No.
Yep.
No.
So slow today, Amanda. No breakfast?
Because it's new knowledge.
Every lesson is new knowledge.
No. Last semester is the...
Old knowledge.
Yes.
That's okay. Can I continue?
No.
I'm continuing, Amanda. Ideal gas laws. Okay, so. Right. Okay, so some of these laws maybe you've heard of from high school, or maybe you'll do them in chemistry. So Boyle's law says for an ideal gas, P is inversely proportional to 1 over V. So I'll explain what that means. What Boyle says is if you have a gas and you make the volume smaller, so for example here the volume divides by 2, so if this was say 10 meters cubed, this will be 5 meters cubed. He said the pressure should increase. So if the pressure here was 20 pascals, Boyle says the pressure here should be 40 pascals. That if you divide the volume by 2, the pressure should be multiplied by 2. So if the volume goes down, then the pressure goes up. Or if the volume goes up, the pressure goes down. That's what inversely proportional means, this relationship. So he says P is inversely proportional to 1 over V only if the temperature and the mass stays the same. So don't change the mass of the temperature. So as a formula, you write it like this. P is inversely proportional to 1 over V. Or another way to write it is that PV is constant. Yeah? No. In the last question of your homework, was the PV constant? No, it wasn't. It was different in each one. So why do you think Boyle's law doesn't work there?
Because the volume was different.
No, not to do with the volume. So Boyle says that the temperature needs to be the same. When you press the gas down, the temperature goes up. So this is why it wasn't constant. Okay. That P multiplied by V doesn't change. It's constant. Now in the homework this wasn't true because the temperature of the gas was changing. Yep. Continue. So it'll not surprise you to know that temperature and pressure are related. What do you think the relationship is between temperature and pressure?
Increase.
Increase the temperature, increase the pressure. Yeah. And if the volume is constant, yeah. So from our day-to-day experience, we know that if the temperature is increased, then the pressure will increase. Until kaboom. You know this. You keep heating something, the pressure will increase until kaboom. Your popcorn exploded, or whatever it is you're doing. So below is a graph of the pressure and the temperature. So as the temperature increases, the pressure increases. So maybe Grace is making popcorn, Sophie is making, let's see, rice, and Amanda can be making, making what? I missed that. What she's making? Oh, okay. Dumplings then, or something. Or whatever. Or, Amanda has hydrogen, Sophie has helium, and Grace has oxygen. And they notice that when they increase the temperature, what happens to their pressure? It increases. So the graphs go up. However, all three graphs, they all go back and meet at the same point. Doesn't matter what the gas is, or if it's dumplings, hydrogen, helium, oxygen, popcorn, rice, whatever, doesn't matter. The pressure increases, but all the pressure lines meet at the same point. I'd like the graph.
What do you mean at meeting same point?
What do I mean by what?
The same point.
Yeah. So, the red, the blue, and the green ABC lines, they all meet at the same point. They all come together and meet at the same point. Yeah, what's happening there? I'll explain. Yeah. Did you draw this? Yeah. So if we take something like this, if I heat this, what happens to the pressure? It increases. So let's say this is A. So you see the points on A? They're different points for different temperatures. If you draw a line, it goes back down to here. Here, what's the pressure at this point minus this temperature?
0.
The pressure is 0. What happens if you go past this point? What happens to the pressure? It's negative. Not possible. The pressure should be positive. So this here is like the limit. It can't get any smaller.
Cannot be negative pressure.
Can't have negative pressure because then, I don't know, it means the water turns inside out or something. Yeah? You get, yes, no. What's wrong?
I didn't get the last Tuesday.
Right. So what I'm saying, at this point here, minus 273 Celsius, the pressure is 0. We cannot go past this point because the pressure then would be negative, which is not allowed. Yeah. Because then if the pressure was negative, it means the water is sucking things in, which we don't want. Okay? So this point here is the same for every graph. The water, the gas, whatever. So this makes us think, maybe this is the coldest anything can be. It's the limit to how cold anything can be. So you can't be colder than minus 273.
Is it true?
And it is true. So this is called absolute zero. It's the coldest temperature possible. You cannot be colder than this. And this you will do in chemistry for sure, if you haven't done it already.
So, what's the temperature of liquid hydrogen?
Temperature of liquid hydrogen, oh, I don't know, it'd be like about minus 270 or something. Impossible. Can't be lower than this temperature. So this is the coldest temperature possible. It's called absolute zero. minus 273.15 Celsius. Yes? Celsius, C. Like, you know, today is 10C, 12C maybe?
What is, do you use F or C?
F? Oh no, never. Never.
Today is 7C.
I don't understand F. I only understand C. Yes. What is it today? 7. Nice. 7C. Nice. Okay. Continue. Yes.
Not nice, I can't get up.
Yes, I know, it's a problem. Now, sometimes I just say minus 273, but it's really minus 273.15. I can't remember what it says in the exam book to use, but it says it in the exam. Okay.
So minus 273 is Kelvin, right?
We'll get to that shortly. So absolute zero is the lowest possible temperature any material can be at. Therefore, we'll use a new scale called Kelvin, which is the same as Celsius, but, and here's the big difference, increased by 273.15. That is, temperature in Kelvin is temperature in Celsius plus 273.15. This you will do in chemistry for sure. Yeah. Yeah, so what the meaning is, Celsius, that's the C. So today, the temperature is, what did you say, Harin? 7 Celsius. Yeah. So the temperature is 7 Celsius or 280 Kelvin. Kelvin is a different way to measure temperature. You remember we have F, C, and now K. So for example, you could say 7 Celsius is 280 Kelvin. Yeah? Yeah, K. Yeah. Why do you think we use Kelvin? If it's so similar to Celsius, why bother using Kelvin? Any idea? No idea?
Because Kelvin is, the 0 is the least it can be.
Yeah? No, okay. Kelvin is always positive. There's no negative. Because what's the smallest Celsius? Minus 273. So the Kelvin is always positive. What's the smallest Kelvin? 0. So this is why to use Kelvin. Yeah?
So why did they come up with Celsius? Why didn't they use Kelvin?
Because they didn't know about Kelvin when they knew about Celsius. So you know when Fahrenheit, Celsius, Kelvin. Yes. Okay, got this? Yep. Okay.
No, why didn't Celsius die like Fahrenheit died?
I think because if I told you the temperature today was 280 Kelvin, you'd be, is that good or bad? You know, it's easier to picture Celsius because 0 Celsius is ice and 100 Celsius is boiling water. Yeah? So it's easier to understand. Okay. By using Kelvin, the temperature is always positive. So this is why we use Kelvin. One of the reasons we use Kelvin. The most important reason, actually. Okay, so next thing we need to do. How do we count in physics? So you know how to count. 1, 2, 3. 1 student, 2 students, 3 students, okay? Do we count like this in physics? Well, we need to have a unit. So imagine we have some water. We do not say, for example, we have 10 to the 23 molecules of water. We use a unit to count. You don't need to write this. You don't need to write this. So, for example, you know bakers who make cakes. They count in 13s. Farmers, they count in 12s. Did you know this? No. Yeah, you do know this. So, for example, if you have 12 eggs, you know that's called a dozen. 12 eggs? I'm sure you have this in China too. No? South Korea, do you count like this as well?
Yeah.
Farmer counts in 12s.
Pencil case.
yeah, I know.
蛋当
Yes, okay. So farmers count in 12s. So they go 12, 24, 36, etc. Okay. Bakers who bake cakes, they count in 13s. 13, 26, 39. Did you know this one?
Yeah, the
No.
baker's one is harder than
Bakers count in 13,
Why?
farmers count in, I don't know why, farmers count in 12s. Yeah? In physics, we count in some way like this as well. So bakers count in 13s. So 10 bakers' dozens is 130, for example. In physics, we count in units, but units bigger than 13. Because in physics, you know, the molecules, there are many molecules. So we need to count. We don't count in 13s. We shall use something called Avogadro, which you should know from chemistry. Too much pressure. Right. You know Avogadro from chemistry. Yeah. So a mole of something, cups of coffee, stars, whatever, is 1 Avogadro. And 1 Avogadro is this much. So I just need you to write down the definition. In physics and in chemistry, we count in moles. 1 mole, 2 moles, 3 moles. Avogadro constant. Yeah. Yes. 6.02 times 10 to the 23. That's 1 mole. Is this much. So, for example, if you have this many eggs, which is a lot of eggs, you have 1 mole of eggs. Yes, you won't have this many eggs. Yes. So, for example, here is H2O. You know H2O? So maybe in this bottle there are 10 moles of H2O. Okay. You've done this in chemistry, right? Lorraine has said Avogadro before? I think so.
I forget.
Okay. You think you've done it, right? Maybe?
Yeah, I forget.
Okay. So, if I have 1 mole of H2O, or 1 mole of cups of coffee, or 1 mole of stars, then I have 6.02 times 10 to the 23 molecules of H2O, 6.02 times 10 to the 23 cups of coffee, it's a lot of coffee, and 6.02 times 10 to the 23 stars. So 1 mole is just a lot of anything. Yeah? Okay. So imagine I have 1 mole of cups of coffee. A lot of coffee, right? What would the mass be? Okay, so I want you to try and calculate the mass of a mole of coffee, cups of coffee. What's the mass of 1 cup of coffee?
500 to 100.
Well, it depends if you get venti mocha or if you get small americano. So we'll go with
250.
we'll go with small americano.
More.
Yeah, so 250 grams. Yeah. So can you calculate the mass of 1 mole of coffee? So for example, what's the mass of 1 cup? 250. 2 cups? 500 grams. You know? So you just need to multiply.
250, right?
250 we'll go with. You get an answer?
1.505 times 10 to the power 26.
So you get this. A big number. What did you get? 1.5
505 times 10 to the power 26.
kilograms.
Grams.
Oh no, make it kilograms.
1.505 times 10 to the power 23.
Did you get it, Sophie?
No.
Okay. So what I did, all I did was the mass multiplied by how many I have. So this is the total mass in kilograms. 0.250 times Avogadro. That's the mass, just multiply. Yeah?
It's the mass of molar mass.
No, yes. This is the mass of 1 mole. So this is called the molar mass. The mass of 1 mole. Yeah?
Oh, molar mass.
Yes. Sounds familiar? Yes. Okay, continue? Yeah. Add just the example and the word molar mass. So the molar mass is the mass of 1 mole. Please note, it's very common to use grams instead of kilograms here. This is what you do in chemistry. Yeah? Okay. Continue. So for example, the molar mass of H2O, does anyone know it? I don't think.
16 plus 2, 18.
About 18. So the molar mass is about 18. So that means 1 mole of H2O will be about 18 grams.
So this one should remember.
No, it's just an example. Notice again, grams per mole. Yeah. Now I know in chemistry, Harim,
Yes.
you say it's 18. But in physics, we need to be more accurate than this. How did you get the 18?
Oxygen is 16 and hydrogen is 1.
So add them together, you get 18. It doesn't work like that in physics. It's roughly 18, but it's not exactly 18. In the exam, they'll give you the molar mass. You don't need to use a periodic table to find it, like in chemistry. Okay? What's wrong?
Look at your Casio 991.
It's nice. Yes, it's useful. I told you you should buy one.
Yes, but I
Many
saw
times.
on Amazon,
Yes. You want one, yes?
but I don't know how to use it.
Okay. Continue. So please note, important, we use big N for the number of molecules and small n for the number of moles. Now this is how I remember. Big N is bigger than small n. Okay? So big N for the number of molecules and small n for the number of moles. So if you want a formula, you can see here, the big N is equal to the small n multiplied by Avogadro. But you probably saw that in chemistry. Maybe. Maybe?
And maybe Molar Mass.
If you want. I don't use a LAR. MA if you want. NA or MA? Wait, what are you talking about? No, NA is Avogadro. Yeah, NA is Avogadro. 6.02. Yes. Continue. Okay. So, hint to remember, big N is bigger than small n. Right, so we have a little bit more to do still. Let's have a look at one example here. Now, I want you to do this one by yourself because I think this could be like a chemistry question as well. I think it's a good idea if you do. Okay, so can you do the first one? How would you do the first one? How many moles of H2O are there?
Oh.
What would you do?
Mass of
Correct. And what's the mass? 1 litre. So what's the mass of 1 litre?
1 kg.
1 kilogram.
Then change it to grams.
Change it to grams. So how many grams is that?
1,000.
1,000. So then 1,000 divide
By
18.01528. And what do you get, Harry?
55.5.
55.5. So the answer to the first part is 55.5.
What's the phone?
Have a look at this. Tell me what you think. Show Sophie as well. Does that make sense? Andy, did you get number 1? Yeah, makes sense. What did you get? 55.5, yeah?
5.5.
Yeah. Yes. Amanda? Yep, okay. Right, how can you do part B?
Just times the mole with the Avogadro.
Yeah, moles multiplied by Avogadro's number. So can you multiply my answer by Avogadro's number for part B? Yes? It's big. 3.3 multiply 10 power 25. Got that? Oops. Yes? Okay. Part C. How many hydrogen atoms? Yes? 2? Just only 2 in total?
6 point.
No, how do you do C? How can you do part C?
Times 2, right?
It's 2 multiply,
3.6.
yeah, the last answer.
Yeah.
6.68 times 1025. Grace, you multiply the answer in B by 2. Yes?
It's 6.68.
Look.
No, I know.
You know? Okay. Okay.
How to write down the formula?
Yeah, you would say the mass is 1,000 grams. The molar mass is whatever, 18 grams. So the number of moles, that's the N, is 1,000 divided by 18, which is 55.5 moles. That's the N.
Wait, so the answer for C is just times 2, right?
Yeah. And then the answer for D
It's the same.
is the same. Yeah. This is for A. Then for B, big N is small n multiply Avogadro. And then for C, the answer is 2n, big N. And the answer for D is whatever 1n is. Because you have H2O, you have twice the H, and the O is only once. Is that okay? What? No, I need to. There's nothing interesting here. You know this from chemistry.
Yes. But M, you said is the number of moles. Nothing.
Continuing. Right, so let's go back to Boyle's law. So Boyle, it won't surprise you to know that there are other relationships as well. So we know that pressure is inversely proportional to volume. And then what do we say about pressure and temperature? Increase, decrease. So pressure is proportional to temperature. Volume is proportional to the number of molecules. So if you have twice the number of molecules, then twice the volume. Pressure is also proportional to the number of molecules. Volume is proportional to temperature. So, I mean, you can write these down if you want, but don't write down the English, just write down the relationships here.
How do you write the middle of the letter?
Proportional, and it's like this.
It's different.
It's close.
What is the big M?
Number of molecules. Number of moles. Continue. So, it looks like all of these are coming from the same formula. You know, they're all very similar. And the answer is yes, they are. And the formula is called the ideal gas law. And it's PV equals N or T, where or is a constant. So wait, before you write this down, let me just explain why this formula. So for example, imagine that the N, the or, and T are constant. Yes? They don't change. If the pressure goes up, what must happen to the volume? It must go down. This is Boyle's law, isn't it? Now, imagine the volume, the N, and the or are constant. Yes? If the P goes up, then the T must go up as well. You know, so what I'm saying is, all of these relationships, they come from this one formula called the ideal gas law. And or is a constant, and we'll explain that value, or we'll give you the value in a minute. In fact, I think you do this with Lorraine also.
Yeah.
Have you done it?
Yes.
Are you doing it already? Oh, right, okay. Well then, do you know the value of or?
Yeah, but
Yeah, but what?
I remember.
8.
Yes?
3, 1.
Yes.
What are
It's a constant, just a constant.
okay.
What's the unit for or? Do you know the unit for or? PV equals N or T. So or equals PV over NT. So the unit for or would be, well, this one here, Pascal. Yeah, if you want to do Pascal, but I don't want to do Pascal. But do you remember we showed that PV is the same unit as joules? So this is joules per mole. per Kelvin. And you must use Kelvin now.
Is R?
This is the units, yeah, the units for R. Joule per mole per Kelvin. Yep. Continue? No?
Okay.
Yeah. Right. So you remember the value from chemistry for ore, it's 8.31. Yeah. But I'll write that on the screen in a moment. Now, this is if you use...
Oh, no.
Yes, no, it is this.
No, I remember R is 298.
No, 8.31. It's on the calculator. It is...
MRT
8.31 is the ore. Anyway, continuing. So, look. You can have PV equals nRT, but remember you have big N, number of molecules, equals small n, what's small n? Number of moles, multiplied by Avogadro. So, if you want, you could say small n is big N divided by Avogadro. If you put that in here, you can say PV equals big N over Avogadro or T. Or if you want, you can say PV equals big N or divided by NA T. And please note, this is also just a constant. So do you see what I mean? You have two formulas if you use moles or molecules. Oh, I just forgot to say, maybe you know it actually. What's the name of the constant ore? Do you know what? It's not. Does anyone know its name? Somebody knows its name. Does anyone know its name for the ore?
Maybe Patrick.
Anyone? What about if I said ideal gas law constant?
Is that the name?
Yes. That's the name. Okay, so I continue. So, what? No, I typed something wrong there, sorry. Let me fix that before I give it to you. Okay, that should be NKT. So, in Lorraine's chemistry class, do you use moles or do you use molecules in your formula? Moles. So that means you use or. But if you use molecules, then you should use this constant. And this constant people call K for short. I don't feel like you need to use it because, you can still use this formula, but you just need to change the N into big N by using Avogadro. But if you want, you can call this constant here K, and this one has a name, which we'll get to. Let me just reopen this, please. once it's ready. It's stupid. It's really stupid. All K is or divided by Avogadro. That's all it is. It's this is K here. So you can say NKT. Okay, so let's open this back up. Alright. Come on, there we go. We were, let's see. Here. Okay. So we can have PV equals nRT or PV equals nKT. If we use molecules, we must use K here. But all K is or divided by Na. There's nothing special. Let's check. So we check the dimensions. Or, what do we say or was? Joules per mole per Kelvin. And for K, it'll be the same, except it'll be joules per Kelvin. No moles. Divided, we see they're the same formulas, with just a different constant if we're using different units. We call or the ideal gas law constant, and we call K the Boltzmann constant.
Wait, unit for K is joule per mole. Okay.
Joule per Kelvin. And K is called the Boltzmann constant. They are really the same thing, just with different units. Why do we need two constants? After all, if PV equals N or T, then PV equals NA or T. Did I write that one down right? Yes, yeah. Since N equals NNA, I don't know. I don't know why people have the formulas in two different ways. I don't feel it's necessary. Let me explain really clearly. So, for example, do you have a formula for if you use, you have your distance, speed, time? Do you have one formula if you use meters and one formula if you use kilometers? No. It's the same formula, just different units. You know what I mean? Here, we have two formulas, but they're really the same formula. It's just which unit you're using, So if you're using moles, you can use the first formula, and if you're using molecules, you can use the second formula. But you can just use the first formula if you change molecules to moles, So I don't know why there's two formulas. It feels unnecessary.
So we need them to remember this?
You can just remember one of them, and then you can change from moles to molecules or whatever. But in the exam, they want you to know both.
So in the exam, I should write down two different...
No. In the exam, you can use either formula. But the exam might ask you to give both formulas. You need to know both for the exam. I don't remember. I'll have to check. So anyways, I don't know why there's two formulas. Ask a chemistry teacher. But we can clearly see that or equals NaK. Anyways, this is all very boring. I'll just give you the two values for or and K. So you know the or, you know this one from Lorraine's class. And the K, here it is here. Yes. Got the constants? They're also on the calculator, if you have this calculator. Hold on. The R is constant 27, and the K, where's the K? Maybe 25, yeah. I'm looking at Avogadro's there as well. NA, Avogadro.
What is Molar?
You don't have this, do you?
What?
I think you do. Where are you going? So watch. Look, you type shift 7, and then if you want the K, you type in 25, and you get it on the screen. You should buy one. You should buy one. Okay. Continue. Hey, finally. Hey, important. Red alert. Always use Kelvin for these formulas. Look in red. Always use Kelvin for temperature in these formulas.
So not use degree.
Not in my class, don't. Let's use Kelvin. So, from now on, it's safer just to use Kelvin. Okay. I need to go on. So, here are some molar mass values. So, for example, water, carbon dioxide, hydrogen, helium, oxygen, nitrogen, and so on. So, just because of the time, can you just maybe, you can either take a picture on your phone or watch the video later, but leave some space to write these values down, okay? And then we'll do an example, and then we'll finish. Okay. You need these for the homework. Right. I think again, just to save time, because I realise we're nearly finished, can you leave some space to write the question down, and we'll look at the answer now. So just leave some space. You can take a picture if you want. Okay, so I'll draw what we have. So for this question, what you have a tank. So you can draw this. Its height is 1 meter. The radius is 30 centimeters. The temperature is 26.85 Celsius. And the pressure is 3 atmospheres. And the first question is for the helium. There's helium in the tank. Helium. Alright, so first thing, yes?
If it's 3 atmospheres, it's 3 times 1.
Yeah, the first thing we need to do is change this into pascals and change this into Kelvin. So, Grace, can you change this into Kelvin?
What?
The temperature, 26.85. You know how to change to Kelvin?
Yeah.
And Hareen, can you give me this pressure in pascals, please?
The radius 0.36.
0.3.
304.09.
30 times 10 to the...
Oh, yeah, sorry, times 1000.
Temperature, Grace?
300.
Exactly 300. Yep, nice.
304050.
304050 pascals. Okay. And also, from the table, the helium is, molar mass is 4 point, we'll just say 4 to make it easy. The molar mass for helium is 4. So the molar mass of helium is equal to 4 grams. Okay. A. I want to know the how many moles. So if I use my formula, PV equals N or T, then N equals PV over RT. So this is how many moles are in the tank. Can you calculate that for me, please? So we know the P. Do we know the V?
No. Yes.
Well, we could know it, yeah. So let's see what we get. Let's see. P 304050 times V, which is pi r squared times the height, over R, which is 8.31, and the T, which is 300. So I got 34.5 volume. V is pi r squared h. Okay, how can I get the number of molecules of helium?
Mole times Avogadro.
Yeah, so if I multiply this by Avogadro, yeah, here's the R here. Yeah. .08 times 10 to the 23 molecules. Moles. See? Yeah? No? Huh? A? Yeah, oh sorry, A123, I should say A123. Yeah, so this is A1, A2, and then A3. How many atoms are in the tank of helium? No. Helium is only one, it's not in pairs. Yeah, so this one here is also 2.08 times 10 to the 23 atoms. Okay, B. Some gas is escaped and the new pressure is 2 atmospheres. So if you look here, some gas came out and the pressure is now 2 atmospheres. Do you understand? So the question is, how many moles are left in the tank? So what you do is you recalculate, but the pressure is not 304050. The pressure is now 202700. Why is the pressure? It says here, some gas escapes and the new pressure is 2 atmospheres. Right, so if we use our formula, N equals PV over RT again, this time will we get more or less than 34.5?
More.
Less?
But pressure is less.
23 basically. 23 moles. So therefore, Therefore, 11.5 moles escaped. Do you understand? Because there's 23 inside now, so that means 11.5 moles left. Here, it was 34.5 moles, yes? But the new moles is 23. So where did the moles go? They went outside. How many went outside? 11.5 moles went outside. Does that make sense? I mean, is that okay? I don't know. Do you do this in chemistry?
Something similar.
Similar? You know, like if there was 100 moles and now there's only 90 moles, then 10 moles left. Okay, so what is the volume of the helium that escaped? So here I want the volume of the gas that came out. So that's part 1, now part 2. PV equals N or T. V equals N or T over P. Now, do we know the N?
Yes.
What is the N?
11.5.
11.5. Do we know the or?
Yes.
Yes, what is it? 8.31. Yeah. The constant, 8.31. Do we know the T? Yes, what is it? 300. Do we know the P?
Yeah.
Yeah, what is it?
2 or
No. Now, what's the P now?
outside.
It's outside the tank, so what's the P?
101.
The P is now 1 atmosphere because it's outside the tank. So, 11.5 times 8.31 times 300 over 101.35 kilo, and we get 0.283 meters cubed. Question, Grace, yes?
No.
You sure? There it is. It's okay? I know I'm going fast. There was a lot to do today. Yeah?
How to translate temperature to
Plus 273.15. Last part. So in the last part, the tank is left open, so all the helium escapes. But actually, there's still a little bit left inside. Let's work out how much is left inside. PV equals N or T. So there's still a little bit left. It's actually very difficult to get all the helium out because if you took everything out, then it would be empty and then everything would go into it. Yeah. So there's still a little helium left in the tank. How much? N equals or T over PV. Do we know the or? Yes. What is it? 8.31. Do we know the T? Yes, it's 300. Do we know the P?
Yes.
What is it? 1 atmosphere. And do we know the volume? Yeah, it's pi r squared h for the tank.
But I thought it's outside now.
No, we want to know what's left inside. Our question is what's left inside. Right, so 8.31 times 300 over 101.35 times 1000 times pi times r squared. So there's 0.087 moles left. And if you wanted that as a mass, that's around about 0.34 grams. Because remember, the molar mass was 4.
But then N is in PV over PV over.
Ah! PV. I did it again. PV over RT. Sorry, I'm going too fast. The N is 11.5 moles.
But isn't the molar mass 2?
No, that was 4. I wrote it at the start. 4.
Isn't it in real life 2?
Um,
Because it's the second one, right?
yeah, but it's 2 protons and 2 neutrons.
Yeah, right.
I think it's 4.
Yeah.
Anyways, 46 grams is the mass. Molar mass is 4 grams. Grace, it's in the table actually back here. Helium is 4 grams, the molar mass. How did I get which? Oh, this number multiply 4.
Oh, 4, yes.
Yes? Sleepies?
I think it is something to...
Is there no homework?
There is. Yes. Look, I know there was a lot to do, and I was hoping that your chemistry knowledge would help you. Maybe I was hoping too much. Yes, okay. Alright, so the homework is not as bad as my example. The homework is shorter than my example.
Which one? Shorter tongue to be more larger.
Yeah, this is it now. These questions are like section A, and this would be like section B. So this is like a section B, and this is like a section A. Okay.